Hello, everyone. Welcome to the summer 2025 version of Computer Architecture, CS211 for Rutgers University. I'm your professor, Dr. Burns, and I'm going to go ahead and get it started for this class. So let me go ahead and share my screen. All right. All right, so this is lecture 2B. And what I'm going to do is I'm going to kind of pick up where we left off before. We're still kind of in the basics for the computer architecture overall, hardware interface, and how that is impacted by our software, etc. So we're going to go over today is the von Neumann model, Amdahl's law, why we use C, and then I'm also going to show you guys how to log into ilabs. That is actually an I. Let me just update that right now. So ilabs is where you're going to be doing the majority of your work. Anything that you do for this class, especially if it's C code, will have to work in ilabs. So keep that in mind. I know that we prefer, a lot of us prefer using VS Code or Virtual Studio or other platforms, as do I. But it will have to function on the ilabs machine. So keep that in mind as you do your project and different programming assignments. All right, so we talked about a bunch of components. We talked about the ISA last week. We talked about, I'm sorry, not last week, but in the last lecture, we talked about just general hardware and different things like that. So as we know, we're familiar with the operating systems. They really serve as like a supervisor for this interface between your hardware and your software. And what that means is that they are going to determine which application gets the software, and your operating system is going to run side by side with those applications. In order for someone, if Python says I want to do this, or it says I want to talk to this component of your hardware, any API, it will have to get permission from the operating system in order to do that. Now, as we talk about a lot various components for our computer architecture, one of the things we want to remember is that if we want to enhance a computer system or anything you want to do really, you always want to start with kind of a model and a plan. So for computer architecture, one of the most famous models is the von Neumann concept. And what this does is it allows us to kind of envision computer architecture overall and how the data flows in order to provide improvements. Now, some of the functions of the von Neumann architecture is that, yes, it's going to model your data flow, meaning if I'm going from memory to my hard drive to some other item, what does that look like in terms of the overall system and how that flows among the other components? Now, one of the essential features of this particular item is that this model is that it has one memory space. All right. Now, there are some architectures like the Harvard architecture that have two memory spaces, but this one uses one. Which makes it a lot simpler than some of those other models. And it makes it a little bit easier for you to kind of digest and really grasp how the things flow between different components of this computer. Now, because it has one memory space, what that means is that programs and instructions are stored on the same memory bus. For this, it's a model, right? Keep in mind that this is a model. But in this model, programs and instructions are represented in the same space, and they are stored in the same memory. Now, the key concepts or the key components of this are going to be your CPU and your ALU. Now, for some, the ALU is a part, in some models is a part of the CPU, and that's fine. And by the way, CPU, central processing unit, your arithmetic logic unit. So you can put them together, or you can put them in one. Or you can separate them, CPU, ALU, the memory, and then your input and your output. If you were to get this on the exam, those are going to be your four components: input, output, ALU, CPU, and your memory. All right. And of course, your input output devices are going to be what you see that allow you to interface with your computer. Now, if we look at this conceptually, this is kind of a model of that particular diagram. Notice how it is showing you this flow between the data. Your memory is this huge stage that we get to play on. Right? A lot of instructions or your the data that you're going to get is going to be stored in your memory, right? But not everybody is going to have direct access to that memory. So this kind of shows how the data is flowing back and forth between memory, between your processing unit, the control flow, and then your input device. All right. And like I was saying before, sometimes these two components, let me go ahead and get my annotation here. These two components here, sometimes they are kind of put together. Now, why is this model? Why do we care about this? And why is this significant to what we're doing? Well, for one thing, it really sets a foundation for how you want to represent computers, right? And it's still foundational even for the modern architecture that we have now. Some of the principles that we have here help to design, to guide some of the systems that we have today, right? Because I know this is how my data is flowing, then I know what I want to do to decrease this time between the main, this huge memory here and my control unit. If a lot of the processes are going between these two, right? So this has to happen before everything else happens, right? I can visualize this now, and now I need to know, okay, I need to find a way to increase the speed of these processes so that everything else on the outside of the system operates effectively, right? So this allows us this model to kind of see it and help us to really improve those systems. It also has an influence on programming and hardware design, and just overall how your computer functions. Now, as we go back to, I kind of showed this slide in the first lecture, 1A. And as we go back to this, I want you guys to keep in mind and think about some things here. Um, that there are going to be three sections that are going to be critical for an effective computer design. And that's going to be your power, your processing, and your memory, right? These are the three areas that are critical that most designers and engineers are thinking about as they are thinking of how can we improve this computer. So what we're going to talk about now is our power component, right? How can we make how long can a program run? And then how much power does each process require? The more processes you're doing, the more you're going to drain your battery. And the faster you're going to need to either charge it or replace the battery, depending on how long you've had the computer. So one of the things that you want to consider with that is something called Moore's Law. Now, right, I talked about this. This last item really talked about is how much does how much power does a process require, and how long can my computer run, right? So Moore's Law is a concept that discusses basically transistors, right? And the basics of this concept is that he said he estimated that transistors will double every 2 years. So he developed this, and I will talk a little bit back in the 60s, and he estimated that based on how computers were growing and enhancing, that there would be a double in transitions on the chip each year. He also kind of predicted that there would be exponential growth in computing. And with this, as these components get smaller and smaller, as the transistors increase, that means that it has more ability, and there will be a decreased cost for these particular computers. So let's talk a little bit about the history of Moore's Law, right? It was developed by Gordon Moore from his original observation of transistors and computers overall in 1965, and then in the early 70s, it was really implemented into these microprocessors. So that's where you kind of see the expansion and the growth of these computers, right? So he said, okay, this is what's going to happen, and then this was able to be used. Like, if I know that I can double the components of the transistors in there, that means I'm going to vastly improve my processing and the functionality of my computer. In the 1990s, that's where you really see the rise of personal computing. Now we talk about, or a lot of times, we get things like cell phones and different things after it's been out for a while. Typically, the government has it first, and then it comes down. Those that are richer have it, and then it comes down more towards mainstream. So now in the 90s, you see this rise of personal computing because, as more predicted, the computer components and things got a lot cheaper. Now, a lot more people are able to buy it. And access it from like everyday people. So we see the rise of personal computing in the 90s, right? That's where you see like all the iMacs, and you see like IBM, and you see all these companies growing and really enhancing and promoting the ability to have personal computers. And then, of course, in the 2000s, where we are now, that's where you see these mobile devices and even things beyond that, right? You have all your cell phones, you have your tablets, you have your laptops, etc., right? So that's kind of the progression of this and how Moore's law, in terms of transistors, has progressed, and we've seen that growth over time. So let's kind of define Moore's law a little bit more, right? Oh, I'm sorry, I did this slide already. Okay, so I'm actually, let me just go ahead and delete this now. All right. What are the implications of this for us? Right. So I want to, because I want to make sure this all connects. We talked about power. What are the implications of this Moore's law and transistors and all that on our power? And what are the implications of it in computer design overall? Well, because of these what this states and us seeing this in practice, we know that as these transistors get smaller and smaller, it's easier to um, kind of get them into more computers, which means you're going to start seeing a reduced cost. So you're going to see reduced sizes in computers overall, right? Remember back in the 60s, you might need like an entire room to hold a gigabyte of space, right? And now we see it on a chip that's like this small, right? So we see reduced size, and of course, with better manufacturing, you're going to see reduced costs. Now, in addition to that, because of the role of transistors, right, by doubling them each every 2 years, or basically increasing the number of transistors, now I'm able to process and make more decisions within a shorter time frame. So now I see that I can do something with this and really have AI advancements, right? Because AI is based on neural networks, or the ability to make several decisions, right? Your computer's going to be all binary decisions. So the more transistors I have, the more networks and the more refined I can make my neural network, which is the basis for your machine code, machine language, excuse me, which allows us to have these AI advancements. Now, what it also means is that as I get smaller and smaller with these transistors, and as I put more and more on a chip, I'm coming up against heat dissipation issues, right? How small can I make it? And if I'm putting more into a smaller space, that means I'm going to be taking up more heat and using up more energy. So now we want to consider power consumption and how that implies with what we're doing. So the question is, what do we do with all this, right? How do we as engineers, how do we as computer engineers, how do we change this, or how do we respond to that? Well, if we're concerned about this power dissipation, or power consumption and heat dissipation, we can do a number of things, right? We can limit the number of transistors used, right? That means that I'm not going to be using all of these transistors at once, but I'm just going to be using them, one at a time, or not one at a time, but section by section, depending on what process I'm doing, right? We can also stagger the powering of cores so that I don't have to turn everything on at once, right? That's going to also help us to decrease some of that power and that heat dissipation. And we know that you can write parallel programs to coordinate between these different devices, these different transistors, and the different processes that are happening. And of course, from a hardware perspective, implement better cooling solutions. The cooler you make it, the less hot it gets, and the less power it's going to consume. Now, what we see currently in some of the semiconductor stuff is we see even a more of a going and a rolling towards 3D transistors, right? If I can put, instead of just having this two-dimensional device, can then I make it a three-dimensional device, right? Which would allow me to have more complicated or more complex algorithms and more complex decision making, which would vastly improve the AI trends, right? And there's also the emergence of quantum computing, right? I'm sure we've heard about that. There's a little bit of a focus onto more energy efficient designs. How can I make this better in terms of energy? And how can I, if I want to have this AI, how can I really get that onto a chip design, right? I don't want to have to figure out where all of these are laying out using human methods, but I already know the basics of it. Let me just plug that into an AI machine, and then you go ahead and tell me where that layout needs to be in order to provide the best response for my power and also for the signals that are going through. Now, what we're going to see as we continue with this is going to be innovation in materials and processes. There is going to be limits to miniaturization. I mean, we could only get so small. So at some point, it's going to be like, okay, you can't just keep on making these smaller and smaller. You're going to reach a physical limit. And we want to think about different computer paradigms and how we want to be more sustainable and environmentally conscious as we do these designs. All right, so that was power, right? When we do these transistors, how can we kind of reduce the power? How can we reduce the heat and just make it a little bit better as we are going through, right? Now let's talk about the second item on the list, processing. How fast can I do this? How fast will my program run? Right. I don't want to be waiting. If I'm gaming, I don't want to have this slow response time. When I send in an email, I don't want to wait seconds for it to go through. If I'm trying to open up a file, I don't want to be waiting several seconds, right? How fast can I do these processes? And how many tasks can I handle simultaneously? Well, that's going to depend on multiple things, but one of the things you want to think about is your clock speed, your performance, right? The faster my CPU is, the faster I can typically do some of those tasks. So how do we do this? How do we improve that? And how do we do some of the calculations associated with that, right? How do we know conceptually and theoretically what to expect in terms of improvements uh, for these particular items? Well, one of the ways we can do that is by something called Amdahl's law. Now, Amdahl's law is basically it was formulated by this guy Gene Amdahl in 1967, right? So we see around the same time that Moore was had came across this theory. Amdahl also formulated a theory for specifically for timing, right? And describes the speed up of a task when you have parallel processing. Now, keep in mind, if you're doing things in parallel, or if it's not just 100% based on the computer, that means you're not going to get 100% improvement. If I were to double the processor, that doesn't mean I'm going to get twice the speed, right? It depends on what you're doing in parallel and how much that particular item is going to influence the device. Now, what this theory does is it really focuses on it and it puts this in a perspective or from like using sequential portions of that task, of the task. This is significant for various reasons, right? It shows that as you keep on adding processors, really eventually your returns are going to be diminishing, right? It's gonna you gotta get to a point where it's like, okay, I can add all these processors, but eventually you're not gonna get much more improvement. It also enhances this thought that, hey, you don't want to just do one improvement, but you want to do several sequential tasks that maybe you can improve. And it helps to define and guide resources as we think about parallel computing. So let's go ahead and look at the equation for Amdahl's law. Amdahl's law is given by this equation that you see here. And each of these components, you have your total speed up factor. That means by what factor am I speeding up this computer, and the percentage of time that the part is used, and then the speed up of the part. So for example, when I'm talking about processors, right? How often or what is the percentage of time that that processor is being used? Now, I say the part because we may get to a point where your processor is not going to be the fully determining factor in it, right? Once you get your processor up to speed, it may be something else like your memory or something else in your hardware that you need to optimize in order to speed up your computer overall. So this is one way and one form that we use for our computer. And let's go through some of the equations for this. Let's think about this. Let's say you have an enhancement that runs 4 times faster than it did on the original machine, but it's only used 60% of the time. What's going to be your speed up that is gained from this, right? So let's remember our equation and what these symbols stand for. Now we are given this, and we already know what we're looking for is the speed up factor. What is the speed up gained by this? The percentage of time that this process uses is 60% or 0.6, and then the speed up time of the part is 4, right? It's 4 times as fast as it used to be, right? So when we plug all of this into this equation, this is kind of what we get, right? We're going to say, okay, I already know 1 minus 6. Now keep in mind that this equation, that 1 minus p, so p, that means what the time that is kind of doing in your particular action in parallel to what you're doing to everything else. So that 1 minus p, right, means that everything else is going to take up 40% of that time. So I'm always going to have that there. And this is going to be the thing that then decreases. So from that, I see that my speed up factor is 1.81. Right? So even though I'm increasing or enhancing this by 4 times, the overall system is only seeing a speed up factor of less than 2, right? So that shows you right there that depending on what process you're improving, you're not going to get a one-to-one enhancement for doubling your processors or cutting your memory access time in half. So let's look at another one because we talked about that. What if we wanted to get the new program runtime, right? We're going to use a very similar equation. I know that I have 2 processors, which means my speed up factor for this particular component is 2. It says I'm using this 40% of the time. So that means that my P percentage is 0.4. The first thing I need to do is determine the speed up factor. If I determine the speed up factor, then I can calculate the time, right? So again, we can plug this in relatively simple into our equation, and we'll get a speed up factor of 1.25%. Now, next thing is, okay, from this, how do I get the time, right? So you can take a similar approach with saying, okay, if I know I want to get the time, what was my estimated time? Very simple mathematically. If I know my original time, my estimated time, I can take my original time, divide that by my speed up factor, and boom, I got whatever my new time is, right? So that's super simple. You can do that algebraically. And if we plug that in here, we'll see that our original time, the new time is basically now 2 hours faster than the original one, right? And that gives us a good way to run that calculation. So we have our speed up factor, which means how much are we speeding up the computer overall, the total process overall. We've also been able to determine what the new timing is after I've done that process. And there's another thing that we might want to consider as we go through this, right? And that is calculating the number of processors. So what if I wanted to do this in reverse? What if I give you and say, hey, I want to cut down this time by 5 hours. How many processors do I need to add, right? And that would be a real question that you wanna ask in your computer, right? 'Cause it's a very similar thing if you think about, okay, how much, um I'll give you a good example. If I have my computer, I had one of my older computers, and I was like, well, I really want to increase the speed of it. So I think I had maybe 8 gigs of RAM and I doubled the RAM size, right? What do I need to do to get more a quicker process or quicker application, right? So you may be asked, what do I need to do to how many processes do I need to improve it by a certain amount of time, right? You want to consider this is going to be very similar, our estimated time. And this again is based on Amdahl's law. It's just a reformatting of the original law that we talked about. Your serial fraction, and then your parallel fraction, right? Serial fraction meaning what am I doing from a perspective of just it being like one item, and then the parallel portion, which is 1 minus s, which was the original one up here, and then the number of processors is what you're going to get out of that particular equation. All right, so let's kind of put this into practice. All right, so let's go through and look at this. All right, here's our equation, and if we're trying to determine the time, I'm going to bring my annotation information over here. All right, I think I want this as black, that's fine. All right, so I know that my new time is going to be 15. My original time was 20 hours. Now, if I have one process that runs 40% of the time, that means my parallel portion is going to be 0.4 because that is what I'm doing in parallel, which means my serial portion is going to be 1 minus 0.4 or 0.6. All right. So that means the rest of my machine is operating the other 60% of the time, right? And then finally, what else are we missing? Percentage N. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4. N is what we're solving for. So that's our big question mark here, right? What is N? All right, so let's go ahead and plug in these values to kind of get what we want. All right, I already know I said this is 20. Oh, I'm sorry, that's actually not 20. That is 15. 15 is my goal, and that's going to be equal to 20, which is my original time, times my serial portion. I already said that's going to be 60%, plus my now if my number of processors stays the same, then we already know that that's going to be 1, but it's not. So we have 0.4 divided by whatever my processors are, right? All right. So I'm going to just do some quick conversion over here. If I bring this and I divide both sides by 20 over here, we'll make that blue. If I divide this by 20 to get rid of that, and I'll also divide this by 20, then I know that I'm going to have um, 0.75 over here is now going to be equal to the rest of this stuff, right? Now, once I bring that down, I can subtract the 0.6 from over here. Sorry, let me just take it slow because it's gonna look messy if I don't. All right. The reason I'm taking time to do this is I want you guys also to do the same thing, a demonstration of how you're doing these calculations rather than just plugging it in. So that's why I'm taking this tedious time of doing and going through and flowing through this. All right, 0.75. I can bring this down here. Zero 0.4 over n. Then once I bring this over to this side, I know I have 0.15 because I'm going to subtract that. That's going to be equal to 0.4 all over n, right? So I can say n then is going to be equal to 0.4 over 0.15, which ends up being 2.67 approximately. So the number of processors I need is 3, right? End up needing 3 processors because, of course, you can't have a portion of a processor. So my final number, right, my final count of processors is going to be 3. All right, so hopefully that all makes sense. Oh, shoot. So 3 processors there. Uh, is it gonna let me move? Okay, 3 processors are gonna be my final one. All right, so let's go ahead and clear all of this and go to the next portion of it. We know that 3 processors are needed. If you were to do another example, and you guys can go ahead and do this as part of your homework. If you're doing this same example, how much do you need to reduce the time to 10 hours? All right. Now, what we want to know about this is what are the applications in the real world? Well, Amdahl's law is going to help us as we go through kind of this supercomputing options, right? When keep on increasing the processors or I keep on increasing a certain task, how much is that going to help me improve the other stuff? It assists with cloud computing and determining what you need in terms of your different elements, and it also helps with our data processing. All right. Finally, last but not least, let's talk about memory, right? Which is our third item kind of on these important factor scale. For our memory, there's something called a memory wall, right? So we talked about power, we talked about processing, but it gets to a point where what's going to be the most critical portion of that, if we go back, if you guys remember that von Neumann structure that we were talking about, that memory part was a huge portion of it, right? It was huge, right? And that's because memory is so vital. Everything that you need to do, you're going to need to pull that from memory. What commands am I sending? Well, I have that somewhere stored on memory. What data am I getting? I have that somewhere stored on memory, right? So the questions are generally how much space do I have, and then how often does it need access? The memory wall is basically stating that as you increase capacity, you're not going to increase in performance. And here's why. Not always. You get to a point where you don't always increase in performance. And here's why. If, for example, you are a person that loves shoes and you have 10 shoes and there's 2 pairs that you really, really like, right? You can easily go in, or there's 1 pair that you really, really like. You can easily go in and find that pair because I have a small capacity. I only have 10 shoes. Now, let's say you get rich, you buy a lot more shoes. So now you have 10,000 pairs of shoes, much larger capacity, much larger thing to choose from. But now, in order to find that 1 pair of shoes, it's going to be very, very hard. So it's going to take you more time to sort through all of your things and find that 1 pair of shoes. That's kind of where you get to this memory wall or this capacity increase, but not a performance increase. Because now I'm taking so long to look through this massive collection of shoes or this massive collection of memory that I'm not really getting the performance I want because I'm spending time looking for items in my memory. Now, one way to resolve that or to mitigate that is by adding a cache. Now, a cache is just a small subset of memory that you use often, right? It's between your main memory, right, which was at that top that we saw in our von Neumann architecture diagram, and the actual processing, right? It's between your CPU and the main memory, meaning I can actually go to this one. It's a lot smaller. And if I'm using it often, right, I might take those pair of shoes and put them in the front of the closet, right? So I know what I want and I can pull that out more often than what I have in this larger area of memory. And what that does is it allows me to access things a lot quicker. We see that everybody caches when you look at in terms of your website. Google, I'm going to add all this cache and all of this stuff. And sometimes it messes us up because it's storing all these things in memory and you have to clear it. But the benefit of it is that the next time you go to that page, you can get there a lot more rapidly than you did when you initially called that page. So that's what we'll talk about. And what you want to consider this concept because you're going to be designing a cache. How can you improve that and enhance that, and maybe determine what you're going to get into in that cache before you actually pull out the data. Now let's go into a little bit more of some of the program language types, right? And why we use them. Machine language. Now, keep in mind, we talked about the von Neumann, right? We have the memory, CPU, input and output, right? Memory, CPU, input and output. Your memory, your CPU is going to understand binary code and binary code only. So your machine language are basically a bunch of ones and zeros. It's closest to the hardware, and it has instruction for the CPU directly, right? It gives direct instructions for the CPU. Now, it's also going to have the shortest execution time in comparison to the other items. When we look at assembly language is a human readable version of machine code. Now, the disadvantage of this is that it needs to be converted to binary code before it can be used. But it has more control over binary code. Like, I'm not going to understand a bunch of ones and zeros, but I can understand kind of this human readable portion of assembly code. And it's also important because your assembly code is going to have a shorter execution time than your high level language, and it's going to be a little bit closer to the hardware as well. And then high level languages, that's going to be human readable. It's going to need an interpreter or a compiler. Now, it's more versatile than it contains functions, but it does have a longer execution time. Meaning, if I say print F, it's going to take a little while to actually carry out that function because that needs to be compiled, interpreted, and then sent to the actual CPU in ones and zeros. So if we look at some of the examples here, of course, zeros and ones from machine language. When we look at assembly language, some of those, the things that are used to write that or some different language types would be like COBOL and BASIC and Fortran, which are still used in some components. And it has the ability, if you know how to program in it, that's great. But we really look more now at these high level languages, right? C, Java, JavaScript, HTML, CSS, right? All of these languages that we already understand, we can write a function in, and then that it's compiled, and then later, after it's compiled, it is interpreted by your machine language or your CPU, excuse me. Now, what we use in this course is, of course, C. And I want to talk a little bit about why we use that. So C has a clearer interaction with hardware. So why C versus Python or JavaScript or Java is because C has more interaction with the hardware than you would with Python or those other languages, which are going to need a little bit more of a compiling and interpretation before it operates. You could see a little bit more of what you're doing with the hardware. You see much more of the interactions with memory and how you're pulling that. You can call a specific memory address and see, and you can send those commands. You can even, in some instances, kind of directly talk in terms of machine code to really have that direct interaction with the CPU. It allows low-level code, like I talked about when we talked about assembly language. C is going to allow you to do that low-level coding, and it can manipulate the hardware and the memory directly. Now, why we want to understand that for hardware interaction is because memory management, just like I talked about before, we often talk about processors and how we can increase our processing capability, but your memory is so vital in the operation of your computer, right? So if you understand that hardware interaction and how you can do memory management, you're on a better road to designing a more effective computer, and also designing programs that run faster, right? The faster the more you understand memory, the better you are going to be at determining how to best access and use that particular memory. Also, knowing and understand pointers and references, super vital. It's very frustrating initially to learn it, but once you get it, you'll really understand how my computer sees from what I'm getting from there's an input and an output, right? And the computer is only seeing a memory address, but you're telling it to get something in data. Like you have a variable or an item in mind, right? So when you understand your pointer and reference and how you're referencing that in code, it'll better help us understand the computer system overall. Also, using C will really help you reinforce your concepts of data structures and different things at a lower level. And you can really gain insight into some of the system calls and different things you would use with like APIs. All right, so now we're going to shift a little bit and get to something that's a little bit more intriguing. Let's go into ilabs login. ilabs. Okay, so in order to access ilabs, you can do this in a couple of different ways. Okay, now, first of all, ilabs is basically a series of computers that are available to Rutgers students. Those computers are based on a Linux platform, and you have the ability to access them remotely and do a bunch of coding. Each time you log into an ilabs computer, you can not only access just that one, but there's several. And we're just going to look at the site that you can get into. So first thing you want to do is you want to go into, there's a few ways you can access it. So one way is to absolutely go into, sorry, let me pull that up. One way is to go into this site here. So sorry, guys, so sorry. All right, weblogin.cs.rutgers.edu. So that's the first way I'm going to show you guys. And that's going to take you to this Apache guacamole type thing. And you need to use your username and ID to username, which is your net ID, and your password to get in. Now, if you don't have a password, like it says here, you can go ahead and create one in the account. It is not the same password as your standard Rutgers login. So you have to create, it's a separate account. You have to create it. So spend some time creating it. Your first assignment is going to be logging into ilabs, proving that you logged into that, and creating a very simple C code. So you want to make sure you can access that sooner rather than later. I'm going to go ahead and log in. Of course, all of my information is saved on here. So it allows me to access and log in here. All right, now what you'll get to is you'll see all of these computers that are available to you for using at your pleasure, right? These are your ilab machines here, 1 through 4. I would recommend working with the first 3. ilabs 4 has a different version of Ubuntu or a different version of Linux. So we're going to use one of these 3 so that everybody's kind of on the same platform. There's also other computers that are available here that you can see and access if you wanted to. But for today, let's go ahead and go into ilabs 3. As soon as you open it up, what you'll notice is that it's going to come up with, well, hopefully it does. And sometimes the ilabs machines are slower than I want them to be. Okay, so it will come up with this Linux platform. This is if you come through the Guacamole Apache system here. And when you get to this platform, then you can open up like a terminal and do whatever you want to do here. So I'm going to open up a couple terminals. And this is where you're going to do a lot of your kind of programming here, right? Now, you want to become familiar with Linux commands and what they're doing here. So if I open up my terminal, I can see, you'll see that it has my username, identification, and it's also telling me the device that I'm logged into. I'm going to ignore that message. And then I can see every time you log into ilabs, it will show you what's available on your desktop. So if I go up to activities here and I would pull out like a file system, just so it looks a little bit more like what you see on Windows. File manager, right? So if you'll see here, you'll kind of see all of my documents, desktop, and all of those things that I have associated with this. Every time you log in to your ilabs machine, or every time you log into the system, your home or your desktop and everything will come with you. Right? So here are like some of my classes and stuff. All right, so let me get out of that. Now, I can also access that here. Now I'm going to go into, I have a folder for this already. Um, and then I'm going to go into this. All right, so now I'm in my CS211 class. You'll see where I am here. I'm going to clear all that out, and I'm going to make a folder for, I'm going to call this 2025 SU, and then I'm going to CD into that. All right, so now I'm in this folder. There's nothing in there. And if I wanted to, I could go ahead and start my different programs as well. So I'm sorry, I did show you guys one way to log in. That's if you go to this web login.cs.rutgers.edu. If you wanted to do a remote host into that, you can also do that. I use something called if I want to do SSH into something, I use something called mobile extern, but you can use whatever, platform you want to use. There's more popular ones. I kind of like this one. But if you wanted to do a SSH session so that you didn't have to go to Guacamole, you can do that as well. So I'll go ahead and show you guys. I'm going to show an example of that. If I wanted to do a new session, I'm going to SSH into this. You just give in your username. Oh, I'm sorry. Actually, you're going to specify where you want to log in. I'm going to do ilabs1 cs.rutgers.edu. And my username is going to be TLD95. Oh, actually, no, I'm not going to specify a username. I'm just going to have it log me into this system. And what I want to use is, why don't we use 4? All right, it's going to pull up this. It's going to give me that, and that's fine. Then here's where you would put in your particular username and my password. Choose to save it. And now you'll see that I am logged into this on ilabs 4. And if I do an LS, you'll see that it has the same screen as I had previously. So if you wanted to remote in this way, you can do that as well. And I can CD into that same teaching directory that I was in previously. And now I'm in that same directory that I was in before. Now you'll notice that everything that I'm using here are Linux commands, right? That's something that you can use very if you aren't familiar with it, you want to become familiar with it. CDs, change directory. MKDIR is going to be where you make your directory, you make your folder, and then here's where you, if I would do an LS, that's going to list everything in that particular folder. All right, I'm going to go back to where I was previously. Now, I am in this particular folder, and if I wanted to, I can do a C code in order to do that, but I think I'm going to actually cover that. I'm going to stop the lecture here for now, and I'm going to go over C code and different things in the following lecture. So I hope you enjoyed your time, and I will see you guys in lecture 1C.